So in this lecture, I want to look at the reactions we had been looking at with benzene and use slightly more complicated benzenes. So these would be reactions of substituted benzenes. Now we're not actually going to introduce new curly arrows, but we're going to look at the influence that various groups have on the reactions of benzene. So let's remind ourselves that if we take benzene and we react it with Br2, we need to add a catalyst, and we like iron tribromide because then the halogens match, and we substitute or replace a hydrogen with a bromine atom, and we get HBr as a byproduct here. Now there's an interesting experiment we could do. Let's say we take toluene instead of benzene. So toluene is again methylbenzene, and repeat the exact same reaction conditions, except that for simplicity, let's say we have an excess of Br2, and we could use an excess up above. Turns out that we still get that product out. Okay, so by an excess, I mean like 3 equivalents, not a bajillion equivalents or molar ratio amounts. And we add FeBr3 to this. What we see is that when we're not limited by stoichiometry, toluene has bromination here, here, and here. Interestingly, these two sites have no reaction with bromine, and so those remain hydrogen atoms, plus we get HBr times 3. Okay, so we could have 3 Br2s, whatever. Okay, so that's an interesting outcome. The only product that we obtain is one with 3 bromines that were added. And so what we say is that, well, toluene was able to react 3 times with Br2. It sort of overreacted with Br2. We couldn't get it to react just once. Okay, so that's interesting. Now, the other thing that's interesting is that no reaction occurred at the meta position, or the position meta to the methyl group. And that's indicated by my NR arrows at the meta positions of the product. Okay, just pointing out that we didn't see any bromine substitution there. It's not like it overreacted everywhere. It stopped at just the ortho and the para positions. Now, if we do the exact same reaction but without a catalyst, we can go back to our mono-substituted products. That is, if we react our methylbenzene with Br2, we can add 1 bromine atom. Now, what's interesting is you can get 1 bromine atom across from the methyl product. So this is our, what we say, our para product. And you can see that the methyl and the bromine are oriented next to each other with a para relationship. They're across the ring. If they're right next to each other, that's an ortho relationship. And we can put it on either side. I'm going to draw them just this one time, but please note that with the ortho products, there are 2 ortho and meta positions, and they result in the overall same structure because you can just roll them around. So we get a para product and an ortho product. Now, what did I do differently in this reaction? Well, I omitted the catalyst. So we don't have any catalyst present in this reaction. So what can we say or conclude from this outcome? We could first say that toluene is more reactive than benzene. Okay, so toluene is more reactive than benzene. Number 2, toluene is selective for reaction at the ortho and para positions. okay? So what we notice is that with our substituted benzene, we see a difference in the rate of the reaction and a difference in the type of products that are formed. So the big takeaway I want you to gather at this point is that substituted benzenes have different rates of reaction with our and they don't have to be super electrophiles in some cases. As we saw, we were able to react with Br2. That's sort of a normal electrophile. We didn't have to activate it with the catalyst. Okay, now conversely, if we do the same thing with acetone, or excuse me, benzophenone, excuse me, that's actually acetophenone, but don't worry about the name. Let's just get the structure in front of us. I just ran out of room down here. Let's do an ester, okay, just for simplicity. All right, so if we take this same molecule, let's not worry about the name, and we react this with Br2, it turns out that this is a very slow reaction, even with FeBr3. It's slower than the reaction with benzene. It's slower than the reaction with benzene. Now, additionally, we don't see multiple products form. Rather, we just put the bromine atom at this position. So we just replace here, or you could draw it on the opposite side, but also in the meta position. So meta only, and I'm going to write or. Okay, so when we use this different benzene molecule that had a, in this case, an ester, we don't have to worry about the ester name. It's just a different group, a different thing that's attached to our benzene ring. We get a different rate of reaction. It's slower than the reaction with benzene. Now, additionally, only the meta product was formed. And I show two depictions because both sides of the both metas are the same. So we form one product. You could draw it. You could show the bromine added to either side. Only the meta product was obtained. Okay, so what we see from here is that some substituted benzenes react more slowly. Okay, so we see different rates of reactions and we see different selectivities. And with different selectivities. So we have this selectivity issue and we have this rate issue occurring when we add things on to benzenes. And that introduces the whole idea of substituent effects. So I'm going to scroll up. I'm going to write substituent effects. So substituent effects have to do with how groups, which are our substituents, can alter the rate of a reaction and direct the selectivity. Okay, now a key way of thinking about substituent effects is to think about what they do to the electronics of a molecule, or how they influence the electrons that are reacting within a molecule. These happen to be electron donating or withdrawing substituents. electron donating or withdrawing substituents. These are groups, i.e. substituents, that either ... donate electron density, or sort of electron clouds. Just donate electron density / negative charge to the reaction center. And these are our electron donating groups. This is in contrast to those that withdraw electron density. Or add a positive charge. So you can donate electron density or have a negative charge, withdraw electron density, which would be like if it was a positive charge, it's going to start to suck electrons towards it, from the reaction center. And these are our electron withdrawing effects. So we have two effects. We have electron withdrawing, or electron withdrawing substituents, I should say. Sorry, let's have some parallelism. So we have our electron withdrawing substituents and our electron donating substituents. So both of these do the opposite things to the reaction center. They could add electrons to the reaction center or take electrons away. Now that's kind of a fuzzy idea, whether or not we're adding or withdrawing electrons. And it's best to just to start to move into examples. So let's look at some examples of electron donating substituents to start. Okay, so the electron donating substituents, we could have varying degrees of electron donating groups. The examples would be, for strong electron donating groups, we have an oxygen directly attached to our molecule, a nitrogen directly attached to our molecule. And these are two good examples. For medium, we have an alkyl attached to our the rest of our molecule. And then if we wanted to look at electron withdrawing substituents, and we want to focus on those examples, we again have strong and medium examples. So our examples would be, our strong examples would be nitro and sulfonyl. So RNO2, RSO3, H, I'll say. There's also carbonyls. Where R is attached to a C double bond O. And that C double bond O could have anything on it. And then we have weak, and I'm not going to put them as medium, I'm going to put them as weak withdrawing groups, and these would be halogens. And they get to start. I just want, as we're going through this, we're going to spend a few lectures looking at these effects. What I want you to recognize is that halogens are kind of weird. Okay, so what I want to do now is, since we've pointed out some substituents, and let me just say that, like, life is easier for you if you memorize these electron donating and withdrawing substituents. And you're just able to kind of recognize them quickly. If you look, we're looking at memorizing 1, 2, 3, 4, 5, 6, 7 things, just like flashcards should do it quickly, like classifying if O is directly attached to a molecule, classifying that as a strong electron donating group. Okay, that's helpful. So moving into our actual reaction that we're studying, which is electrophilic aromatic substitution, I want to remind everybody that in these reactions, the aromatic ring, which is the reaction center, is a nucleophile. So in EAS, which is electrophilic aromatic substitution, the aromatic ring, which is the benzene, is the nucleophile. And this is also our reaction center. Now, this is going to guide our thinking as we understand the influence of an electron donating and an electron withdrawing group on our benzene ring. Okay, so what I want to do is show 3 examples of benzenes that have different substituents attached. So I'm going to have 3 benzenes across here. I'm going to add 1 substituent to each of them. First one I'm going to add is a methoxy group. Second one, I'm just going to basically keep benzene, but I'm going to explicitly write the hydrogen atom. Third example, I'm going to have a carbonyl attached. Okay. So what we have here is we have directly attached to O. What I want you to recognize that as is a benzene with an electron donating group. Okay, now over to the far right, skipping the one in the middle, this is directly attached to not an O in this case, but a carbonyl. I want you to recognize that and interpret that as a benzene attached to an electron withdrawing group. So it's a benzene attached to an electron withdrawing group. Okay, now the one in the middle is benzene sort of attached to nothing. And this is going to serve as our reference point. Okay, so benzene attached to nothing. Now what we say then is that since, sorry, I'll make a page here. What we can do then for each of these is categorize them as being electron rich, electron poor, or electron neutral. What I would say here is that the benzene on the left is electron rich. Because it has received more electron density from its electron donating group. Donating group leads to that being rich. If it's received donations, it's become richer in electron density. Here, excuse me, not here, on the right, the benzene is electron poor. Okay, it's having some of its electron density taken away. Now we'll look at the effect, to see what's happening in future lectures, but don't think of it as though it's missing an electron, as though it's actually been oxidized, and conversely, the one on the left being actually reduced and accepting an electron. I just want you to think of the electron as like a fluffy cloud, where a portion of it is starting to drift a little bit and be withdrawn away from the molecule, in the case of the right structure, the withdrawn structure. And then in the case of the donating, it's had a little bit of its cloud added to by the electrons on the oxygen atom. Okay, now and then this one in the middle is electron neutral because it's our reference point. It's what benzene starts out as. Now, because benzene's the nucleophile in EAS, benzenes that are more electron rich are better nucleophiles. They have more electrons to donate. So what we want to do is we want to look at this and see how well it will react in an EAS reaction, an electrophilic aromatic substitution. To understand this, we have to recognize that point. The benzene is the nucleophile. The benzene adds its electrons to an electrophile during these reactions. And if that's the case, then things that are more electron rich will be faster reacting in an EAS reaction. So that's going to be our rich benzene, the one that has received electron density from its donating group. We're going to see faster reactions with or in an EAS reaction. Sorry for reaction. Here we're going to see this is our baseline or normal reaction. But the electron poor benzene is going to have slower EAS reactions. So the electron-rich benzene, which received its electrons from the donating group, is going to react quickly in an EAS reaction, much more so than benzene, and much more so in the case of being attached to an electron withdrawing group. Now, all of this being said, electron donating groups are often called activating groups. So we could say they are activators or activating groups. Because they result in faster EAS reactions. So faster EAS reactions occur when we have electron donating groups attached to our benzene. And what this results in is sometimes you don't need a catalyst, which is what we saw in the case of toluene, which had just a mild electron donating group in the methyl group, and that was sufficient to cause an overreaction to occur with a catalyst and a normal reaction to occur without a catalyst. Now, what we'll mention, I guess we'll save this in the futures. We'll talk about the selectivity in a future lecture. Let's just wrap this one up by saying that conversely, electron withdrawing groups are often called deactivators or deactivating groups. Because they result in slower EAS reactions. Now, in the case of the electron donating groups, I said sometimes we don't need a catalyst for these. Here with electron withdrawing groups, sometimes a catalyst isn't enough. And no reaction can occur. These aren't great benzenes to do electrophilic aromatic substitution with, because when you they're kind of fun because they give this meta selectivity, which we'll talk about next time. That makes them kind of fun, But in reality, if you like go into the lab with your deactivated benzene, you try an EAS reaction, many times you just won't see any reaction at all. So we could talk about it all day on paper and how we get this different selectivity from our donated benzene. But when you go into the lab, you're like, oh man, this really didn't work. I was misled by Willoughby. So anyway, okay, so that'll do it for this time. We'll talk about why these effects occur and how they impact the selectivity and how groups, the electrophiles are directed to certain points in the benzene in the next lecture.